Have you ever marveled at the engineering leaps that occurred during the Second World War? Have you ever thought who were the leading engineering minds and what was their contribution? Stick around as we delve into one of the most innovative and maverick designers and engineers of the war years. Hi everyone, and welcome back to the Jaxom Talks channel. Sir Barnes Wallis, 1887–1979, a study in structural innovation, engineering descent, and technological foresight. Sir Barnes Wallis was one of the most prolific and distinctive British engineers of the 20th century, a figure whose career spanned the transition from marine architecture to the pioneering edge of supersonic flight. His life was characterized by a commitment to innovative structural mechanics. This led to successes such as the geodetic airframe and specialized ordnance, yet simultaneously marked by bureaucratic opposition and political disappointment regarding his post-war visions. His enduring legacy rests on his ability to integrate complex, multidisciplinary physics from fluid dynamics and ballistics to geophysics to resolve seemingly insurmountable technological challenges. Barnes Wallis was born on September 26, 1887, in Ripley, Derbyshire. His formal schooling took place at Hatcham Boys' Grammar School in southeast London. At the age of 17, Wallis left traditional education, beginning his career in January 1905 at Thames Engineering Works in Blackheath. Crucially, his early professional life was in marine engineering. He subsequently shifted his apprenticeship to J. Samuel White's, a prominent shipbuilding firm located at Cowes on the Isle of Wight, where he trained as a marine engineer. This early foundation, dealing with the structural demands of ships' vessels that must maximize payload capacity, all the while maintaining integrity against immense hydrostatic and bending loads, this established a foundational commitment to structural optimization. This structural perspective, rooted in the efficient use of materials and load distribution under stress, would directly inform his later revolutionary work in aviation structures. The opportunity to transition from the marine world to the nascent field of aeronautics arose in 1913, when Wallis left to join Vickers Limited, working as a designer in their airship department. By the mid-1920s, conventional aircraft lacked the necessary range to serve the vast logistical needs of the British Empire. Recognizing this gap, the government initiated the Imperial Airship Scheme in 1924, placing Wallis's employer, Vickers, in charge of constructing the R-100 airship. Wallis's work on the R-100 was pivotal, focusing on designing the structure of the rigid airship. Airships demand an extreme strength-to-weight ratio in order to maximize buoyancy and payload. This necessity reinforced Wallis's inherent skill set in structural efficiency and material science, pushing him to develop advanced light alloy lattice structures that became the precursor to his later geodetic designs. Wallis's time in the airship division concluded shortly after 1930, when he moved to Surrey. The airship phase of his career was effectively terminated by the infamous R-101 disaster, which was the R-100's sister ship. This led to the collapse of the entire British airship program. Principles of the geodetic construction. Following the end of the airship program, Wallis applied his radical structural theories to the design of fixed-wing aircraft for Vickers. Working alongside R.K. Pearson, who handled the general layout of the aircraft, Wallis focused exclusively on designing the internal structures. This specialization allowed him to introduce a revolutionary concept known as geodetic or geodesic construction, sometimes documented as Vickers-Wallis construction. A geodetic airframe replaced the conventional rectangular skeletal framework. It did this with a space frame constructed from a spirally crossing, basket weave network, made up of load-bearing members. These structural members were formed as geodesic curves, meaning they followed the naturally curved outer shape of the aircraft's body and wings. The genius of the geometry lay in the construction principle. The geodesic curves were arranged to form two helices at right angles to each other. This specific arrangement created mutual structural support. This ensured that the torsional load, when applied to any one member, was effectively cancelled out by the load on the mutually supporting member. The result was a structure that was significantly stiffer, stronger, and lighter than the metal framework methods that relied on complicated internal wooden supports and an external doped fabric skin. The geodetic system true fame came with its application in the Vickers Wellington bomber, followed by the Warwick and Windsor. The geodetic design offered two significant operational advantages. First, the structure resulted in a much lighter airframe for a given strength requirement. Secondly, the entire load-bearing structure was contained within the outer shell. This created a large empty space in the center of the airframe, readily available for payload. The Wellington became the primary bomber of the Royal Air Force at the outbreak of World War II. In the early years of the conflict, Bomber Command faced crippling attrition rates. The Wellington's geodetic construction, however, proved to be an invaluable strategic countermeasure to this attrition. The mutually supporting structure gave the aircraft resistance to catastrophic structural failure from localized damage. Reports documented that Wellingtons could absorb extraordinary levels of battle damage, often returning to base with large sections of the structure damaged or missing, demonstrating superior survivability compared to a conventionally constructed aircraft. Wallis had successfully engineered robustness into the core structure. This reduced crew losses and increased mission completion rates, which was vital for the early phase of the war. The challenges of unconventional ordnance and engineering the impossible. Even as the Wellington proved its worth, Wallis turned his mind to offensive challenges. By 1942, planners recognized that the massive strategic dams in Germany's industrial Ruhr Valley were critical targets. However, it turned out that conventional ordnance was useless. The dams were protected by heavy anti-aircraft defenses in addition to anti-torpedo nets submerged in the water. Wallis conceived of a way to bypass these defenses by proposing a revolutionary weapon he initially termed a surface torpedo, which would skip over the water, avoiding the nets. His initial experiments were rudimentary yet prophetic, conducted by bouncing marbles across a water tub in his own back garden. The resulting bomb, initially codenamed Highball, was a spherical version intended for naval targets. This was eventually adapted into the cylindrical mine called Upkeep for the dam attack. Wallis theorized that the bomb would ricochet across the water, strike the dam face, and then sink to detonate underwater, ensuring maximum effect against the structure's base, hydrodynamics, and the ballistics of Upkeep. The success of Operation Chastise, known as the Dambusters raid, was predicated on the successful integration of complex ballistics, hydrodynamics, and precision flying. The final Upkeep weapon was technically a mine or depth charge, designated Vickers Type 464. It was cylindrical, weighed 9,250 pounds and carried a substantial 6,600 pounds charge of Torpex high explosive, optimized for underwater shockwaves. The central engineering challenge was generating controlled skipping. Wallis determined that the weapon must be dropped from a very low altitude at a speed of 240–250 miles per hour. Most importantly, specialized apparatus designed by Roy Chadwick at Avro was required to impart a high rate of backspin, specifically 500 revolutions per minute, just prior to release. This backspin served multiple, critical functions informed by fluid dynamics. The spin generated lift through the Magnus effect. This enabled a controlled skipping trajectory across the water. The spin ensured the weapon fell slightly behind the aircraft's flight path, protecting the Lancaster bomber from the eventual powerful underwater blast. Upon reaching the dam wall, the backspin ensured the cylindrical device adhered to the concrete surface and rolled down, sinking in close contact with the upstream face of the masonry. Once submerged and in contact with the dam wall, the Upkeep mine was designed to detonate via a hydrostatic fuse set for a depth of 30 feet, thereby attacking the highly vulnerable base of the dam. The integration of ballistics, ordnance, and aircraft weapon carriage represented a profound interdisciplinary engineering feat. Despite the complexity, Wallis was given just 8 weeks to finalize the design for operational deployment after the project was officially approved in March 1943. The development of the bouncing bomb was not simply a technical hurdle. It was a political struggle against institutional inertia. Wallis's concept was highly unconventional, and he faced initial fierce opposition from established leaders within Bomber Command, including Air Chief Marshal Sir Arthur Harris, who famously dismissed the idea as a madcap scheme. The delay in attacking targets, identified as strategic as early as 1937, underscores a 6-year period where the conventional military technology was incapable of breaching the defenses surrounding the dams. Wallis's idea was a disruptive technological push, requiring a multidisciplinary solution that fell far outside standard operational doctrine. Wallis's persistence was key. He ultimately bypassed the resistance by securing the support of Air Chief Marshal Sir Charles Portal, the Chief of the Air Staff, who instructed Bomber Command to proceed with the operation in March 1943. This need for high-level political advocacy confirms a recurring pattern in his career. The maverick inventor was repeatedly forced to act as a political operator to gain project viability, a precursor to the institutional challenges he would face again with his post-war aviation concepts. 617 Squadron, led by Wing Commander Guy Gibson, was assembled and subjected to intensive low-level training to master the exacting demands of the mission. Strategic impact and advanced ordnance, critical analysis of Operation Chastise. Operation Chastise, executed on the night of May 16 to 17, 1943, successfully breached the Man and Eder dams. The immediate consequence was catastrophic flooding that severely disrupted the industry of the Ruhr Valley. The damage below the Man Valley included over 1,250 deaths, the destruction of 12 factories and damage to 94 others, alongside extensive loss of homes, farmland, bridges, and utilities. Water production in the Ruhr dropped by 75% for 6 weeks. steel production losses were significant, amounting to over 300,000 tons across May and June. During the war, the raid was heavily leveraged for Allied propaganda, emphasizing the physical destruction and psychological impact. Historically, however, the strategic success remains a subject of debate. Post-war analyses, such as the Review of the Air Offensive Against Germany by Webster and Franklin, they acknowledged the precision of the attack but contended that the long-term physical outcome was neither of fundamental importance nor even seriously damaging, noting that German production recovered relatively quickly. That said, a deeper assessment reveals that the true strategic value of the raid lay in its non-economic consequences, the diversion of German resources. Hitler was reportedly extremely angry at the failure of defenses and ordered massive reinforcement of remaining dams. The defensive assets deployed, including 10,000 frontline troops, the equivalent of a full division, extensive anti-aircraft guns, barrage balloons, and searchlights were tied up guarding strategic infrastructure. Wallis's invention, therefore, achieved a profound strategic success by forcing a costly, sustained strain on the German war machine through manpower and resource depletion, even if the economic disruption was temporary. Furthermore, the raid was celebrated for its moral and psychological effects, significantly boosting public confidence in bomber command and showcasing precision attack capabilities. The evolution of ordnance, from bouncing to earthquake bombs, the success of upkeep demonstrated the power of achieving structural failure through specialized means. He recognized that the greatest destructive force was achieved not by surface impact, but by utilizing seismic shockwaves generated by explosions deep within or immediately adjacent to a structure. This realization led to his invention of the Tallboy 12,000 pounds and Grand Slam 22,000 pounds bombs, collectively known as earthquake bombs. These colossal weapons were designed with hardened casings and aerodynamic shapes. This allowed them to be dropped from high altitude to achieve supersonic speeds and penetrate deep into concrete and earth before detonation. The objective was for the bomb to bury itself and explode either underground or within a hardened structure, creating an artificial earthquake effect that collapsed targets, such as concrete U-boat pens and deep underground factories, by a seismic shock. This progression reveals the truly interdisciplinary nature of Wallis's genius. He transitioned seamlessly from structural engineering on the Wellington to hydrodynamics of the bouncing bomb and finally to geophysics of the earthquake bombs. His career trajectory is defined by the consistent application of fundamental engineering physics to overcome unique defense challenges. The post-war vision of supersonic flight and variable geometry. After the cessation of hostilities, Wallis returned to Vickers-Armstrongs as the head of research and development. His focus shifted entirely to the next frontier of supersonic flight and high-altitude, long-range transport. Understanding that future designs required unparalleled experimental verification, Wallis oversaw the construction of the stratosphere chamber near the Brooklands racetrack at Weybridge. This massive facility, covering nearly 20,000 square feet, was the largest of its kind globally at the time. The chamber's purpose was to simulate extreme operational environments for supersonic aircraft. It was capable of testing fuselages and components at altitudes of 70,000 feet, temperatures as low as -60 C and air densities 1/20th of ground level. By building this sophisticated infrastructure, Wallis affirmed his commitment to rigorous empirical research, ensuring that his visionary aircraft designs were scientifically validated. The swing wing concept, Wild Goose and the Swallow project, Wallis correctly identified a critical engineering hurdle for sustained supersonic flight. This was managing the immense aerodynamic and center of gravity shifts that occur when transitioning between the subsonic takeoff or landing and high-speed supersonic cruise. In 1946, he published an influential engineering paper, The Application of the Aerodynamic Properties to the Stabilization and Control of Aerodynes. In this, he combined his studies on laminar flow with his proposed solution of variable geometry, or the variable sweep wing. This research led to the Swallow project, Vickers Type 010, a revolutionary concept that succeeded his earlier Wild Goose study. The Swallow was conceived as a wing-controlled aerodyne, meaning it lacked conventional control surfaces such as a rudder or vertical stabilizer. Instead, control was achieved by pivoting the entire wing assembly. The design featured a movable delta wing configuration. It uniquely mounted for engines in pivoting nacelles near the wingtips. This allowed the thrust vector to remain aligned with the direction of travel during wing movement. The Swallow was envisioned as having twin roles, a supersonic successor to the Vickers Valiant V bomber and a groundbreaking long-distance airliner capable of non-stop return flights from the UK to Australia in approximately 10 hours. Between 1954 and 1957, Wallis successfully flew several remote-controlled models, including rocket-propelled supersonic versions, demonstrating the viability of the concept's low and high-speed flight characteristics. the 1957 Defense White Paper that resulted in political cancellation and lost opportunities. Despite the technical breakthroughs and proven model viability, the Swallow project faced an insurmountable challenge: political short-sightedness. The required 10 years of estimated development for the full-scale bomber and transport versions proved too long for the prevailing political climate. The project was fatally undercut. By the 1957 Defense White Paper, this policy document controversially declared that the era of manned military aircraft was drawing to a close, arguing that future defense priorities would be dominated by guided missiles. Consequently, government funding for Swallow was withdrawn in June 1957, leading to the formal cancellation of the project that same year. Vickers was financially unable to independently pursue the high costs of full-scale supersonic development. The cancellation of Swallow represents a profound strategic failure. Britain, who possessed world-leading variable geometry research, chose to terminate the project based on a flawed doctrine. As a minor consolation, Wallis was permitted to engage with the American Mutual Weapons Development Program. This resulted in vital knowledge sharing with the United States, including a joint research program with NASA Langley Research Center in 1958. American engineers analyzed Wallis's concepts by testing simplified models of the Swallow. Despite confirming initial stability deficiencies, this led to major breakthroughs in variable sweep concepts, particularly in eliminating undesirable wing translation. The transfer of this foundational research meant that while Britain abandoned the technology, the concept lived on to become a staple of American and European military aviation that led to the F-14, F-111 and Tornado jets. He was formally knighted in 1968, recognizing a lifetime dedicated to engineering and invention. A legacy defined by structural integrity and dissent, the career of Sir Barnes Wallis presents a compelling study of a perpetual maverick engineer. A prophetic grasp of physical principles from the battle damage tolerance of the geodetic Wellington to the seismic effectiveness of the earthquake bombs. His ability to apply fundamental engineering physics across structural mechanics, hydrodynamics, and geophysics remains unique. Conversely, his greatest challenges stemmed not from technical failure but from institutional and political limitations. This political decision effectively limited his final technological impact on British aviation, forcing the transfer of foundational variable geometry technology to the United States. Ultimately, Wallis's life trajectory illustrates that while technical genius can solve seemingly intractable physical problems, it cannot always overcome political inertia. His enduring technological achievement is the Wellington bomber, but his highest personal aspiration and deepest disappointment remains the unbuilt future of the supersonic Swallow. Which of Wallis's rejected projects do you think should have been built first? Let me know in the comments below. If you have enjoyed this talk, don't forget to like this video and subscribe to the Jaxom Talks channel for more deep dives into the history of engineering. Thanks for watching, and I will catch you next time.